So this will be a short video just to introduce you to the lecture that focuses on pneumatics. So far we've talked about fluid power systems where again, fluids do not create power, but they transmit power. We've talked a lot about hydraulic systems where we can readily calculate the force over a cross-sectional area of a piston that it has a pressurized fluid on the side. So we can put a force in one side and we can get a different force out the other side according to a ratio of the pistons. Pneumatics are another application of fluid power, but they're used in a slightly different way. So pneumatic systems, they use pressurized gas to transmit and control power. They're usually much faster. So a pneumatic system is going to be used for smaller tasks that have to be done lightning fast. So most of your industrial automation where things are equipment is moving like in and out or pick and place types of systems or robotic systems, they have pneumatics. So pneumatics are very practical application of fluids, and they use air. Air is readily available, low cost, safe to use. There's no frictional losses, less mess, no emissions, and they are fast. So I'm going to add on here fast. So when will you use a hydraulic? For a slow application where you need really high forces. When will you use pneumatics is the application for pneumatics is point to point. So you need to pick up something and move it over there, or you need to activate a claw that's going to pick up an object, or you need to activate a part of an assembly line, or you need to move things. So something that has one point to another point action rather than the transmission of large forces like a press. But air compresses a little bit more than hydraulic fluid. So it's not really, you can't make like, say, a giant press that's going to press a car body with pneumatics, because most of the piston stroke is going to be used up compressing the air behind the piston. So we do not use it for precise, controlled applications where you need a lot of force. If the travel needs to be smooth, the output needs to be metered, high forces, we don't use pneumatics. So it is used where the end condition of air is of importance. So cylinder extends, cylinder retracts. Clamping, unclamp, clamp, unclamp, clamp. Rotary tools, hoist, drilling, punching, assembling, riveting, etc. Punching application, where something goes down, punches out a blank, comes back up, goes down again, punches out a blank, comes back up. So very, very useful kind of in those quick operations. If you stand in a manufacturing plant and you hear all of the noise of the plant moving, it's moving parts which generally are on air compressors or are pneumatic systems. So in a pneumatic system, usually there's one large or a series of large air compressors that are one or more sources throughout the entire plant. So the air is piped to each circuit through an air filter. In third year, we're going to talk about the filters and the regulators and everything. And we're going to get into sort of energy management. There's a lot of opportunities. So money saving opportunities in compressed air systems. So compressed air system losses are very costly. If you calculate the amount of money that is spent in compressed air system losses, it actually works out to be the most expensive utility that is used in an industrial process. But we get to this more in second and third year. So compressors, you're going to learn about compressors in a lot of your courses. So this is the general, most basic type is a reciprocating compressor. It's a piston The piston moves up and down inside, whoops, inside the bore. And so look, you can see how this works. So air comes in, then, sorry about that, air comes in, then the piston goes up, and then when the piston goes up, now it's sitting up. Now it's sitting up here. The piston is going to go up because this crankshaft is going to make it go up. It's going to be now sitting up here. The piston moved up here, and now the air is in a smaller volume. So it used to be in this whole volume. Now it's in a smaller volume. So it got compressed, and then the smaller volume goes out. So it must be pressurized. So that's the most common type of compressor. That's what you see on, say, your air conditioning unit. For example, when you pay for the electricity in your air conditioning unit, it's operating a reciprocating compressor. Some that do higher duty, here the air is going into these vanes, and then it's getting trapped in here in a smaller and smaller volume before it comes out. So that's a screw compressor that's used in high, really like a larger industrial application. Here's a vane compressor. The air is coming in here, and then by the time it escapes, look, it's taking up less space, so it is compressed, and that's where it comes out. So every one of your courses, you're going to be dealing with compressors. You'll learn a lot about them in second year and third year. Air receivers, basically it is like a reservoir. We cannot size a system so that exactly the right amount of air in it is in it at any given time. So the air receiver is a reservoir, so it acts like a buffer to kind of make sure that the right pressure of air is always given by filling and emptying this buffer that is called an air receiver. And we'll do some calculations about sizing of air receivers, and that'll be in lecture 6, next week's lecture. You should be familiar with control valves like pressure regulators from your lab, and then and check valves. So in your lab, you should get familiar with these types of components. But if you're not familiar with these types of components, then you can just take my title, do a quick image search or a quick YouTube search about what these valves do. And you should also be familiar with the ANSI symbol for them, which you are putting on in your lab submissions. This is a pneumatic actuator, which again will go from point A to point B. The purpose of a very good application of pneumatics. A rotary actuator, pneumatics aren't just used for linear actuation, they're used for rotating as well. So here, this air will feed in and rotate this actuator, which will continuously spin the shaft. And then you can mount anything on this shaft. So a lot of the tools in a manufacturing environment are actually air tools, but they are rotary air tools. So for example, all of the drills and everything that are on a line are all of those air tools run with pneumatics. So this is a vane type of actuator, and this is going to capture the air, is going to come in here and spin the vanes, and then again you get a rotating motion out as the output of a vane type actuator. Here's another type of rotary motor. Lots of opportunities for industrial applications of rotary motors. This is a cross section that shows how this type of rotary vane motor works. So it's constantly bringing in air compressing it and bringing it out again. More rotary actuators. Actuators require a slightly different type of air volumetric flow rate per application. So there's just an example of volumetric flow rates that work with different types of pneumatic tools. And pneumatics, they operate on the principle of an ideal gas law. So in our course, we are going to assume incompressibility. And I want to take a moment to talk about the ideal gas law. So you can read through this, and there's Boyle's law, Charles' law, and Gay-Lussac's law. And they basically each hold something constant. So, but an ideal gas, I'd like you to remember this, because you really, all you need to know is PV equals nRT. So an ideal gas performs with this relationship: pressure times volume is equal to the number of moles times R times T. Now R is a quantity. R is a quantity. And, N is a quantity and R is a material property, or instead of material, I'll say fluid property. But if you're dealing with the same gas, so same gas, then R is the same. If you're dealing with the same size, so, or same amount, then N, which is molar mass, is the same. So the N is a count of the number of molecules that you're working with in this gas. So basically what you can do is you can say, so what the ideal gas laws look at is they look at the state 1 and state 2 when you go across a device. So for example, a linear actuator or something, or let's say the reciprocating compressor, okay, which is a piston. Well, the piston had a volume V1, and then the air got compressed into volume V2. Well, it had a pressure pressure P1, and it had a pressure P2. So in that reciprocating compressor, I used to have a lot of volume, and then I compressed it to a little bit of volume. That's going to have to equal to, well, the pressure used to be big. No, the pressure used to be small, but I pressurized it so at state 2 it would be large, right? So what this looks at is it looks at like a state 1 and a state 2. So for example, and I'm squeezing it into your lecture note here, reciprocating compressor, it has in, out, right? It used to have the piston down here, and the fluid took up this space, right? So it had the fluid volume 1. This is state 1. But state 2 now let's say this is closed at the top, and this has an inlet and an outlet. Well, in state 2, this piston is way up here because it got moved up, right? So now the fluid is just here. So now the fluid got compressed. The fluid got compressed and it's sitting up there now. All right, so, and it used to be over here. So what happened here? Let's see. This volume 1 and this is volume 2. So I would say that in here, volume 1 is greater than volume 2. And if we were to look at the pressure, I would say that pressure 2 would be greater than pressure 1. So what I'm trying to show you is that we're looking at state 1 and state 2, and what happens to pressure, volume, and temperature between them. Because R is a fluid property, and it's the same property. N is a quantity, and it's the same amount of molecules, so they cross out. So what we do is we say that PV equals nRT happened at state 1, and PV equals nRT happened at state 2. So P1V1 equals nRT1 equals P2V2 equals nRT2. So all the ideal gas laws do, and please try to remember this instead of going through an exercise of what Boyle's law is, what Charles' law is, what Gay-Lussac's law is, which one is which. I don't do that. Personally, I've been working with the ideal gas laws for 20 years now. All I remember about ideal gas laws is PV equals nRT. So you set them equal to each other. You set them equal to each other from case 1 to case 2. Set them equal to each other. If you set them equal to each other, then the N and the R cancel out. So let's look at this example I'm showing you. Solve for T. If I solve for T, T1 equals P1V1 over NR. T2 equals P2V2 over NR. Set them equal to each other because the temperature hasn't changed. Let T1 equal T2. Therefore, then you get P1V1 over NR equals P2V2 over NR. You notice then that NR, since it's the same material and the same quantity, cancel out. That gives you P1V1 equals P2V2, which you can arrange any way you want. I believe we did down here, we did V1 over V2 equals P2 over P1. That is one of the ideal gas laws. Turns out, now I'm looking at it, that one's called Boyle's law, but I don't really care so much about that. That's just me. So every exam I've ever written, if I need to do the ideals gas laws, I just say PV equals nRT. The N and the R cancel out. What do I want? Which variable do I want to get rid of? Which one do I want to relate? So I just showed you how to do Boyle's law. There's an example for Boyle's law. Charles' law, it looks like I took here PV equals nRT and PV equals nRT. These are ones, these are at state 2. So solve for what's not in here, P. Let state 1 equal state 2. So P1 is equal to nRT1 over V1. P2 equals nRT2 over V2. All I'm doing is solving for P2. Let P1 equals P2. Therefore, nRT1 equals V1. Over V1 equals nRT2 over V2. And I could cancel those out. N and R is the same material, it's the same count. So I get T1 over V1 equals T2 over V2 is a nice way to express it. But it looks like Charles' law is usually expressed as, so let's just rearrange this. They want the V's on one side. So that's V2 over V1 is equal to T2 over T1. All right. And that's opposite to what I put in the lecture note here. So I can just easily flip those. V1 over V2 is equal to T2 over T1. But again, all I did is PV equals nRT equal to PV equals nRT. Solve for the variable you don't want, set them equal to each other, cross out the N and R. And what did we call that one? That one's called Charles' law. No disrespect to Charles' law, but I don't usually remember the name of it. It's just PV equals nRT. Here's an application for that. And then the last one, we did PV equals nRT. And we it looks like we let V1 equal V2, substitute in, and you get this, which is Gay-Lussac's law. So those are the ideal gas laws. And for the exit ticket, I'm asking you to please try to, in your own words, relate why on earth does the ideal gas law apply to pneumatics? So give that some thought. Think about pneumatic systems and think about what makes them work and what does that have to do with the ideal gas law. Thank you.